Hello, welcome to this lecture series on electronic properties of materials. This is lecture number 9. In this lecture, I am going to continue the Hall effect. Okay, before going to continue, let me just brush up what is a Hall effect and what we discussed in the last class. See, Hall effect, when a thin sheet of a metal or a semiconductor carrying an electric current is placed in a perpendicular magnetic field. An electric field is set up in the transverse direction inside the material. This is what we call as Hall effect. What is the meaning? You take a thin sheet of metal, okay, and connect the two opposite ends to an external source or external battery through an ammeter, and connect this end and this end with a voltmeter, okay, so that you can measure the voltage across the material, right? And I'm going to call this direction of electron movement as the longitudinal direction. So if I switch on the battery, electrons will move right from here to here. Okay, this is the direction of the electron, right? So when you switch on the battery, you will get some voltage here, and that is called longitudinal voltage. Okay, this is normally observed in any conductor. Now what I'm going to do, switch on the battery, and at the same time you keep this plate in a perpendicular magnetic field, external magnetic field. So this arrow mark indicate the direction of the magnetic force of lines. So this plate is kept in a perpendicular magnetic field. When you do that, what will happen? The electrons experience Lorentz force. Because of that, the direction of the electron changes and it deflects and starts to accumulate, okay, at this edge, right? So electron starts to accumulate here. Equally, positive charge starts to accumulate in the other side, in the other end. Okay, so you will get an electric field, a new electric field is generated, and this is what we call as Hall effect. Now if I connect this end and this end with a voltmeter, you will get a potential, and that potential is called Hall voltage. Clear? This Hall voltage appears only when the external electric field is switched on. When external magnetic field, I'm sorry. So Hall voltage is 0 if the external magnetic field strength is 0. Keep this point in mind. Clear? This is Hall effect. This is what we discussed in the last class, right? And you can measure two resistivity here. One in the longitudinal direction, it is called longitudinal resistivity, and the other resistivity in the transverse direction, it is called transverse resistivity. Remember that transverse resistivity is absolutely due to the external magnetic field. Clear? And I told you in the last class that the transverse resistivity is also called as Hall resistivity. This Hall resistivity is directly proportional to applied magnetic field strength. If I equate this, we should introduce a constant, and that constant is nothing but Hall coefficient. Okay, and using Lorentz equation and Newton's law, we can derive the expression for Hall coefficient. I didn't do that, okay, but derivation is available. Okay, remember this formula. Hall coefficient RH is equal to 1 by NF. Here NF is nothing but number of charge carriers per unit volume, and E is the charge of the charge carrier. See why I am using the word charge carrier? Because in metals, we know very well, in metals free electrons are charge carriers in general. Clear? Whereas in the case of semiconductors, right, the charge carrier may be excess of electrons or excess of holes. Therefore the charge carrier can be either positive or negative, right? That's why I'm using the word charge carrier in general, right? In the case of metals, right, the conduction is due to the free electron. So free electrons are charge carriers in the case of metals. Clear? Good. Now let's continue our Hall effect, okay, in this lecture. So what's the continuation? Listen, what is mean by Hall mobility? Okay, mobility is denoted by the symbol mu. What is mobility in general? Mobility is nothing but drift velocity acquired by the electrons in unit electric field. Okay, so we know very well current density J is given by the formula number of charge carrier per unit volume into charge of the charge carrier into drift velocity. So this product will give you current density. We can also get current density using the formula conductivity into electric field. Conductivity into applied electric field will give J. Right? Since these two J's are one and the same, if I equate these two, I will get an expression like this. What is that? Here the left hand side NF into E into VD, and the right hand side is sigma into epsilon. Sigma is conductivity, epsilon is applied electric field strength. Clear? Now bring this epsilon to the left hand side, keep VD as such, VD by epsilon, and bring NF and E to the right hand side. What is VD by epsilon? This is nothing but drift velocity per unit electric field. That is nothing but mobility. So this VD by epsilon is nothing but mobility. Mobility is denoted in general by the symbol mu. So mu is equal to sigma by NF into E. And we know very well 1 by NF into E, 1 by NF into E is nothing but Hall coefficient. So mobility of the electron is equal to Hall coefficient for the material into the conductivity of the material. If you multiply these two, you will get the mobility of the electrons. Clear? So this is the expression for Hall, and this mobility is also called as Hall mobility. Clear? Good. Now remember, this is very important. RH is nothing but Hall coefficient. Hall coefficient can be measured experimentally. You can measure this Hall coefficient experimentally for a given material. Your material may be metal, your material may be a semiconductor. Whatever it is, you can measure RH experimentally. Clear? And remember, RH value can be positive, RH value can be negative. If RH is positive, what does it implies? It implies that the charge carriers are positive charge carriers. If RH value is negative, it implies that charge carriers are negative charge carriers. Right? You know very well in metals, Drude assumed that, okay, in metals the charge carriers are free electrons. Since electron carry negative charge, therefore Hall coefficient for metals according to Drude model, it should be negative. According to Drude model, RH value for metal should be negative. Yes, it was observed that RH value is negative for most metals, but for few metals RH value also came out as positive. Okay, some metal shows positive RH value, which could not be explained by Drude model. We are going to discuss that under limitations. I am going to say this. Clear? Then Hall coefficient is independent of temperature in the case of metals. Okay, Hall coefficient is independent of temperature in the case of metals. So this is another important information to keep in mind. Right? Now, before completing this, let me work out a simple problem here based on the Hall effect. Okay, just go through the problem. The Hall coefficient for of a specimen is 3.66 into 10 power minus 4. Okay, answer. So Hall coefficient is given. Hall coefficient is denoted by the symbol RH, which is equal to 3.66 into 10 to the power minus 4 meter cube per coulomb. So it is given in SI unit directly. Then the resistivity of the material is given. Resistivity rho is equal to 8.93 into 10 to the power minus 3 ohm meters. We need to calculate mobility and number of charge carriers per unit volume. First, let me calculate NF. Okay, yeah, you know very well how to calculate NF. What is NF? Number of charge carriers per unit volume. How to calculate this? RH is equal to, since this value is positive, okay, RH value is given as positive value, Therefore, I can write, first I'll write the formula RH equal to 1 by NF into charge of the carrier. Since RH value is positive, right, it means the charge carrier should be a positive charge carrier, right? Therefore, NF is equal to 1 by RH value. RH value is given 3.66 into 10 to the power minus 4 into charge of the charge carrier. Positive charge carrier carry a charge of 1.602 into 10 to the power minus 19 coulomb. So here we have per coulomb. This is meter cube per coulomb, and this is coulomb. So these two get cancelled, right? So we have meter cube in the denominator. If it comes to the denominator, you get per meter power minus 3, right? If I simplify this, what we'll get? Let me work out this. Okay, 3.66 I'm sorry, 1 divided by 3.66 equal to this, again divided by 1.602. Yes, the value comes out as 0.1705. Then here we have 10 power minus 4, here we have 10 power minus 19, so you'll get 10 power minus 23. If it bring it to the numerator, you'll get 10 power plus 23. Or I can write this as 1.705 into 10 to the power 22. Okay, so this specimen has a charge carrier per unit volume, as per meter cube, as 1.705 into 10 to the power 22. Remember, what is the importance of this question? If you know Hall coefficient, you can calculate number of charge carrier per unit volume through experimentally obtained value. See, this is very important. Experimentally, you can calculate number of charge carrier per unit volume from the value of the Hall coefficient. Clear? Then second, resistivity data is given. So how to calculate mobility? Let me do it in the next page. So number 2, mobility formula expression is mu, and you know very well mu is equal to RH, okay, into sigma, right? RH into sigma, or I can also write it mu is equal to RH into 1 by rho is nothing but sigma. Okay, and we know the value of RH. RH value is 3.66 into 10 power minus 4. 3.66 into 10 to the power minus 4 into 1 by resistivity value is given, which is given in SI unit ohm meter, 8.93 into 10 power minus 3. 8.93 into 10 power minus 3 ohm meter resistivity value. So let me simplify this. Okay, 3.66 divided by 8.93, yes, it comes out as 0.40985 into here we have 10 power minus 4, here we have 10 power minus 3. If I bring it to the numerator, it becomes 10 power plus 3. So 10 power minus 4, 10 power plus 3, it becomes 10 power minus 1, or we get 0.040985. Okay, this is mobility, right, of the electron. Okay, and the value of Hall coefficient, the unit for Hall coefficient given here is meter cube per coulomb, correct? Meter cube per coulomb is the unit for Hall coefficient, and here we have ohm meter, right? If you bring it to the numerator, you get ohm inverse. Ohm inverse is nothing but Siemens. Meter, if you bring it to the numerator, you get meter inverse. So mobility mu is equal to 0.04098, okay, Siemens meter squared per coulomb. Yes, this is the mobility of the charge carrier in this given specimen. Clear? Yeah, I stop here. We'll continue with the a success of Drude model right in the next lecture. Okay, thank you for listening.